Okay, here we're going to do a little introduction on stuff that's very useful to know. Right, okay, so first of all, we're going to look at sign and magnitude. So this is a way to store negative numbers and positive numbers in a fixed number of bits. And all it means, or the way it works, is the most significant bit is 1 if the binary number is negative, or it's 0, maybe you can guess that, if binary number is positive. Excuse my poor handwriting. Okay, so let's do an example. So if we had 1, 0, 0, 1, our column headings would be 1, 2, 4. Now, the most significant bit is the sign bit. This is called the sign bit. It's not worth 8, it's just called the sign bit. Okay, so this would be positive 1. And then if you had 0, 0, 0, 1, actually, mistake. Right, that would be, I'm sure you spotted it, that would be negative 1. But if we had 0, 0, 0, 1, that would be positive 1. Okay? So that is how sign and magnitude works. Okay. Right, actually, while we're there, what is the biggest number? I think this is a good way to check your understanding. Biggest binary number in 8 bits using sign and magnitude. Okay, so it's going to be the number of, so it's going to be, the biggest number is going to be a positive number. If you think about the numbers, a number line. So we're going to have 0 for our sign bit, because negative would take us on the negative scale, which is smaller than, a negative number is smaller than a positive number, any positive number. Okay, so, and then we need to have 7. 1, 2, 3, 4, 5, 6, 7. So that is the biggest number we could have. The smallest is going to be a negative here, and then all ones. Again, 1, 2, 3, 4, 5, 6, 7. Okay? Right. Okay, so now we're going to look at fixed point. Actually, while I remember, one of the advantages of sign and magnitude is that it's very simple to implement on the processor. Okay, and the disadvantage is it can't store a great range of numbers. Okay, fixed point. Well, now here we're looking at how to store fractional binary numbers. So, say we have 8 bits for the positive. We've got the binary point, and then we've got 8 bits for the fractional part. Okay, so our column headings would be 1, 2, 4, 8, etc. for the 8 bits. Actually, let's put them in just to remove any views. 16, 32, and 64. How many got that? 1. I need one more. 1, 2, 8. Okay, and that is a positive 128. So I'm just going to put a number in here. Okay, and then for the fractional part, it's going to be, the column headings would be 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, and 1 over 128. So that should be a nibble. Yeah, and 256. I don't think I made a mistake there. Yeah, okay, that's right. Okay, so, and then we could have something like this. Okay, all right, so what is the biggest number we could have? Well, all ones. And the smallest, well, we haven't said how to store negative numbers here, so the smallest would be 0. In this case, where we haven't got a way of storing negative numbers. Okay? Right, so that's fixed point. You need to be told where the decimal point is, and by the way, the decimal point is assumed to be in that point, and that's why you don't need to give it in your answers. You shouldn't give it in your answers, because it's not stored there. Okay, now we're going to look at floating point, which I should have talked about after sign and magnitude. So I'm going to call this 1.1. And I should have talked about it here. Okay. All right. Okay, so 2's complement is another more efficient way of storing negative binary numbers. Okay, and if we had 4 bits, the most significant bit would have a negative place value. Okay, so let's look what that looks like. So 1 in 4 bits, then this most significant bit is negative. Most significant bit has a negative place value. Okay. Right, so if we had 1001, if we had 1001 or even 0, that would be -8. Okay. All right, so what is -6 in 2's complement? That's the question. Okay, now if you can look at the column headings and see how to do it, that's fine, but I want to show you another way. So the first thing is, what is 6 in 2's? What is 6? Store 6, so that's going to be that. Now, to make it -6, okay, you need to flip the bits, and then add 1 to the least significant bit. And you'll see why I say least significant bit, and elsewhere you probably hear just add 1. And the reason why I say add 1 to the least significant bit is that when you've got fractional 2's complement, you do need to add it to the least significant bit, which could be not the 1's column. Okay, so right, okay, so let's get on with that. So we're flipping the bits, easy enough. Okay, and now we need to add 1. So 1, I'll put this like this, so we're plussing this. You don't have to lay it out like this at all. I'm just being really clear. So 1 plus 1 is 0, carry the 1. Then that's going to be 1, 0, and then 1. Okay, so this is equal to -6. But let's check that using the column headings. So that would be -8, right? So we've got 1 there, plus 2. So -8 plus the 2. And that does indeed give us -6. Okay, that's 2's complement. Right, okay, and now we are going to talk about floating point. Right, so this will be 0.3. Okay, floating point is a way to store fractional binary numbers in a fixed number of bits. Okay, and the thing to realize is that it is the same idea as something you've already looked at in GCSE, and that is standard form numbers. So let's just remind ourselves, that would be a times 10 to the n, okay, where a must be greater than 0 but less than or equal to 1, and n must be an integer. Okay, so let's look at what that would mean. So if we had 3.142, I wonder where I got that from, and then times 10 to the 2, right? So if we put that in as so that's in standard form, but do you see that as an ordinary number? We would apply this to that. Okay, what does that mean? Okay, so it's times by 2, so this number needs to get bigger, so we're going to 1, 2, so the decimal point would end up here. So that number would be 0.1, no, that's not right. That number would be 314.2, okay? Right, now notice, if we want to put this back into standard form, we have to move the decimal point into a position where this holds true. So it has to be 1, 2, 3. We have to move it into that position. Okay, so it would be 0.3142 times 10. Now we went here 1, 2, 3 jumps, making it smaller. So let's say what we call that minus 3, okay? Right, that was to get it into standard form, but we need to, but that's not the actual number, so this power would actually fix that, and we need to do the opposite, so that power would be 3. Okay, so let's convert this standard form, right? This is in standard form, and let's convert it into a normal number. We're going to apply this to this, okay? So we need it to get, because it's times by 3, so the decimal point will move to make this number bigger, so it's going to move to the right, so it'll be 1, 2, 3, so decimal point in there. So that will be 3.314.2, and we got back to our original number. Okay, so I just did that to show you that floating point numbers are this, you actually encountered this concept of normalization in your GCSE maths. Presumably you had to do that. Okay, so some more language. This is called the mantissa. and this is called the exponent. Okay, so now I just shorten it to M and E whenever I use it. Okay, so generally speaking, it's going to be in this form: M times 2 to the E for binary floating point numbers. Now, this is not stored, it is assumed. And the decimal point here, sorry, the binary point, not stored, because its position is assumed too. We don't want to use up bits because we want to use that to keep the accuracy of the number. Okay, so what does that look like? So binary number, a fractional binary number, might look like this: 1 0 1 0 1 1 0 0, and that and here we have 0 0. Actually, let's do that. Let's do 0 1 0 0, and this number would all potentially be stored together without a gap here. Okay, so what this means is that is going to be 1 0. So that means, I don't have to write all that again because I can write like this: M times 2 to the 1 0 1 0, or M times 2 to the E. That's what that actually means. Okay. Right. Okay, so let's think of some example patterns. So I'm going to go, just to save I'm a bit lazy. Let's say it's 4 bits with a mantissa, and exponent is 4 bits. Okay, so what would that look like? Now, I need to explain something. In a normalized floating point number, the decimal point is always in this position, right? So 0.1, 0, 1. Okay, and 0, 0, 1, 0. Okay, right, and so the floating point, the binary point is assumed here. Okay, and this part is an integer, so there is no decimal point if you conceptually is here. Okay, now both parts, both M and E, are in 2's complement. Okay, so remember that. Now, what I want to tell you is that if this position starts with a 1.0, and it can only do it if it starts like that, then that must mean that the mantissa is negative. If it starts with 0.1, then the mantissa is positive. Okay. Now, so floating point numbers can have a mantissa, normalized floating point numbers can have a mantissa of only these two. Okay? All right. Now, I want to show you a way that I remember this. So, negative m starts with 1.0, positive m starts with 0.1. And I think of this as rotating and becoming the 1 here. And then I know that if it's going to be 0.1, then that is a positive. So with a pair of things, I just have to learn this thing. And as long as I remember 1.0 and the other one is 0.1, the other one must be positive. Okay? Hope that makes sense. Right. I just want to also remind you of some rules. One rule of indices. That 2 to the a times 2 to the b is the same as 2 to the a plus b. Okay. I find the way I do this stuff, that is useful to know. Okay, so hopefully that will all be useful. These little bits of knowledge that often means that that's where the difficulty is when looking at floating point numbers. Okay, now the next thing is we're going to do some questions. Thank you.